Welcome to this lesson on the phases of operations research. Imagine you are planning a massive cross-country road trip with your friends. You would never just jump into the car and start driving blindly without a map or a budget. Operations research works exactly the same way for businesses. It is a step-by-step process that takes a messy, confusing real-world problem and turns it into a clear, solvable mathematical plan. Let us dive in and see how this works. Now that we understand the basic idea, let us look at why this life cycle matters. The phases of operations research act as a crucial bridge between the physical world and the mathematical world. Instead of relying on gut feelings or guesswork, managers use these structured phases to guarantee they are making the best possible choice. The process begins by deeply understanding the real world situation and identifying exactly what needs to be achieved. From there, the situation is translated into a language that computers and mathematics can understand. By strictly following these phases, companies avoid the disastrous mistake of finding a perfect mathematical solution to the wrong business problem. Before we break down each step, let us look at the overall journey. What you are seeing here is a flow chart that visually summarizes an operations research project. Notice how it is a strict sequence. You start at the top with problem definition, moving down to model building, then finding a solution, followed by validation, and finally implementation. You cannot build a model without defining the problem first, and you cannot implement a solution without validating it. This step-by-step discipline is exactly what makes operations research so powerful and reliable. With the roadmap in mind, let us explore the very first and most critical step, problem definition. Why is this so important? Because if you define the problem incorrectly, every single calculation that follows will be completely useless. In this phase, we must clearly identify three main components. First, the objective, which is your ultimate goal, such as maximizing total profit or minimizing total cost. Second, the constraints. These are the strict physical, financial, or time limits that restrict your choices, like having a strict budget. Finally, the decision variables. These are the specific quantities you have the power to change to reach your goal, such as how many chairs to manufacture. While defining the problem, we must also make a crucial distinction between what we can and cannot control. Controllable factors are the elements that the decision maker can directly manipulate. For example, the number of workers you schedule for a shift is controllable, and these usually become our decision variables. On the other hand, uncontrollable factors are external conditions that affect the outcome but cannot be changed by the manager. Think of daily market demand, the cost of raw materials set by suppliers, or weather conditions. A good problem definition clearly separates what we can control from what we must simply accept and plan around. Once the problem is clearly defined in plain English, we move to the next phase, model building. This is where the magic happens, as we translate English words into a mathematical model. A mathematical model is simply a set of equations and inequalities that represent the objective and the constraints we just defined. We use symbols to represent our decision variables and write formulas to show how they interact. After the model is built, we move to the solution phase. Here, we select an appropriate mathematical technique to find the best possible values for our variables, whether that is a simple graphical method or a complex computer algorithm. Now that we know what a model is, let us look at its mathematical structure, starting with the objective function. Conceptually, this formula is the mathematical expression of our goal. The symbol Z represents the total value we want to maximize or minimize, like total profit. The symbols X1 and X2 are our decision variables, representing the quantities of items we decide to produce. The symbols C1 and C2 are the coefficients, representing the profit or cost associated with one single unit of X1 or X2. As the values of our decision variables increase, the total value Z will change accordingly. Our goal is to find the exact combination that gives the best possible set. After defining our goal, we must define our limits using mathematical constraints. This formula enforces the limits of our real-world resources. The symbol B1 represents the total maximum amount of a specific resource available, such as the total kilograms of flour in a bakery. The symbols A11 and A12 represent how much of that resource is consumed by producing 1 unit of X1 and X2. The inequality symbol ensures that the total resources consumed by our chosen variables never exceed the total resources available. If we try to increase X1 too much, the left side of the equation will exceed B1, making the solution physically invalid. After finding a mathematical solution, we cannot just blindly follow it. We must perform the validation phase. Validation means checking if the mathematical answer actually makes sense in the real physical world. For example, if the math tells you to produce -3 cars or to use half of a human worker, the model is flawed and must be adjusted. We also test how sensitive the solution is to small changes in our uncontrollable factors, ensuring the plan is robust. Finally, the last phase is implementation, where the validated mathematical solution is translated back into plain English instructions for the workers and managers to execute in the real world. Before we move on, let us see this with a concrete example. A factory manager wants to know how many tables and chairs to build to make the most money. We begin with phase 1, problem definition. Our decision variables are the number of tables, which we will call X1, and the number of chairs, which we will call X2. The objective is to maximize total profit. Moving to phase 2, model building, we write the objective function. Since each table gives a profit of $40 and each chair gives $30, our total profit Z equals 40 times X1 plus 30 times X2. We want to make Z as large as possible. Now that we have our objective, we must write the constraints for our limited resources. First, the labor hours. We know a table takes 2 hours, a chair takes 1 hour, and we only have 100 hours total. So, 2 times X1 plus 1 times X2 must be less than or equal to 100. This ensures we do not exceed our manpower. Next, we write the constraint for the wood supply. Each item uses exactly 1 unit of wood, and we have 50 units available. Therefore, 1 times X1 plus 1 times X2 must be less than or equal to 50. This keeps our mathematical model grounded in physical reality. To finish building our model, we must add one more crucial element. We must add a logical constraint that prevents negative production, because we cannot build negative tables. These are called non-negativity constraints, written as x1 is greater than or equal to 0 and x2 is greater than or equal to 0. Mathematics allows negative numbers, but physical reality does not. Putting it all together, our final mathematical model clearly states our goal to maximize profit, strictly bound by our labor, wood, and physical reality constraints. The solution phase would then use a technique to find the exact number of tables and chairs to build. Let us look at a second example, where the objective is to minimize something rather than maximize it. A farmer needs to mix a daily diet for his cows using corn and soy, aiming to minimize the total cost. Our decision variables are the kilograms of corn, called Y1, and kilograms of soy, called Y2. Corn costs $2 per kilogram, and soy costs $5. Therefore, our objective function for the total cost C is 2 times Y1 plus 5 times Y2. Unlike the previous example, our mathematical goal here is to make C as small as possible. Now, we must ensure the cow stays healthy by meeting its nutritional requirement. Corn provides 2 grams of protein per kilogram, and soy provides 6 grams. The cow must consume at least 30 grams of protein per day. So we write our constraint, 2 times Y1 plus 6 times Y2 is greater than or equal to 30. Notice we use a greater than or equal to symbol because 30 grams is a minimum requirement. The cow can eat more but never less. Finally, we include the non-negativity constraints because the farmer cannot feed the cow negative kilograms of food. This completes our minimization model. Now that we have built these models, let us discuss why following these strict phases is absolutely essential in the modern business world. If a company skips the problem definition phase, they might spend millions of dollars perfectly solving the wrong problem. This phenomenon is known as an error of the third kind. If they skip the validation phase, they might implement a mathematical solution that looks great on paper but fails miserably in reality due to ignored physical constraints. These phases are used daily by global shipping companies, airlines, and hospitals. By breaking complex chaos into logical steps, organizations save time, reduce waste, and maximize efficiency. We have covered a lot of ground today, so let us review the most important ideas. The phases of operations research provide a structured roadmap for solving complex problems, ensuring decisions are based on logic rather than guesswork. The journey always begins with problem definition, where objectives, constraints, and variables are clearly identified. Then, model building translates those real world limits into mathematics. Finally, validation and implementation ensure the mathematical answer actually works in the real world. You now understand the complete life cycle of operations research. Great job following along, and you are now ready to tackle complex decision making problems.